Yes, yeah, we just did the check, I think, yeah. So, hi everybody, I'm Andy or Andrew Sayer. I like solving inverse problems, mostly in the atmosphere. So first of all, I wanted to say it's a real honor to be sharing the OCI Atmospheres podium this morning with Lorraine, as she's someone who I've looked up to since I came to Goddard in 2010, 12 years ago now, and has also been a consistent source of good and useful career advice. And I think if it had not been for Lorraine, I would have driven myself more crazy than I really am. I also want to acknowledge the Modis Clouds team, because a lot of what we're going to do with PACE OCI builds on a lot of what's been done very successfully for the past 20 to 30 years. Okay, here we go. Great, so I put this picture in so you could see the bottom half of my face, but now I've realized you can kind of see it anyway. This was taken pretty early in the pandemic. My dog's now a lot bigger, and unfortunately my waistline also is. So today I'm going to talk a bit about why we want to do cloud remote sensing at all. And then I'm going to walk through the various OCI products we'll be making at launch from PACE. And I was talking with Jeremy and Lorraine a couple of weeks ago when it came to put these together, and they said, Andy, tell them how the sausage is made. So I'm going to kind of go through programmatically what is our processing data flow and what are the basic concepts behind all of these algorithms. There's a bunch of references I put at the end that you can read, and you can ask me questions today or Friday, or you can just email me later on. So we live on a... I appear to have gone very far forward. Okay, great. The next one is cloud optical thickness. That's just a measure of how strongly is this cloud interacting with light. How strongly does it scatter and absorb radiation? Next is the cloud effective radius. That's a measure of the typical drop size within the clouds. So you can get very small droplets and you can get really big ones, which tend to then rain out. There's the cloud altitude of the top of the cloud, and you can express that in height, so kilometers, temperature, so Kelvin, or pressure, so millibars coordinates. It's just a transform between the three. There's cloud phase, which is saying, is this cloud made of liquid water or is it made of ice crystals of some form? You can also get mixed phase clouds, but we try and pretend they don't exist because they're just very complicated. And finally is this thing called a liquid or ice water path, which is just saying how much water is there in the cloud. And that is a function of the optical thickness and the effective radius. And in true science fashion, each one of these things has these acronyms, which you see dotted endlessly throughout papers and code. So the overall data processing flow we'll be doing for PACE OCI is, like I mentioned earlier, very similar to the NASA Modis and Via's heritage processing system. So first of all, you determine the cloud mask, then you determine the cloud altitude, and then you use that to do the corrections you need to do to get the cloud optical thickness, particle size, and phase from one algorithm. We call that cloud optical properties. And finally, derive the water path from everything else. So in Modis and Vias, the cloud mask is basically a set of multispectral threshold tests. For OCI, we've tried that approach. And we're also currently working on a neural network approach to do the same thing, which I won't talk about. Though if she's here, we have a student, Xingyang Li, who's at UMBC, who's going to start with us in 2 weeks to help with that. So I'm really excited. I don't know if you're here this morning. Yay. Hi. We've only met by Microsoft Teams before, so it's really nice to, I guess we're still a bit distant, but less so. So I won't talk about the neural network today, but maybe next year Xingyang can give a presentation on it if we do this again. So cloud altitude and phase comes next. That's where we have the biggest departure from their heritage. Modis and Vias use thermal infrared measurements to determine the temperature of the top of the cloud. PACE won't have those on any of its instruments, so we're using absorption to determine the pressure. Then we can transform between the two. So this is a new algorithm for us. The next algorithm, cloud optical thickness, is an effective radius. We're running the heritage Modus Vias code directly, which should hopefully lead to a good deal of consistency in the types of products we're getting. And for those people who are already familiar, it will be a benefit because they should be able to get started with PACE differently. So that is the same algorithm. It's in fact the same code, just with some new wrappers on the start and the end. And finally, I won't talk about water path much, except to say that it's a one-line calculation involving a few assumptions based on the other products. So next I'm going to talk through these top 3 algorithms in some detail from our PACE point of view. So the first of these is a cloud mask. Like I say, where are there clouds, where are there not clouds? So here's, I think it's a Modus Aqua image across, yeah, it's Modus Aqua across Europe, again from a few weeks ago. I grew up here where it's always cloudy, and true to form, in the middle of summer it's very cloudy. Yeah. Where everyone is from is always sunny. I grew up in the wrong place, I guess. So again, this is basically a classification. So my true color image, you see the world. The cloud mask image is just, is it cloudy or is it not cloudy? But it's a little more complicated than that. Oh, go ahead.
Could you go back a slide?
Yep.
In the mask, it looks like we can see the dust plume, or does it? It's like a lens. It looks like a smudge.
This?
No, but in the mask image of the right.
Is that haze?
Where?
On the cloud mask side.
Here.
This one, yeah.
That I will talk about in a minute. That is an artifact of the Worldview website's color system, which unfortunately I don't control. So what we have, it's kind of a binary classification, but it's not really a binary classification. There's some probabilistic elements to it as well. So what we get from the heritage, Modus, and Vias products, like were shown on the last slide, is in fact a four-way category. So they don't just say, is this a cloud or is this not a cloud? They say, this pixel is either confidently cloudy, which means I'm really sure, probably cloudy, which means I think so, probably clear, which means I think it's not a cloud, or confidently clear, which means I'm pretty sure this is not a cloud. And what was on that last slide, they colored the probably cloudy very similar to the confidently cloudy, but not identical. And if you look at this Modus image here over the ocean, there's some clouds, there's some sun glint here. Confidently cloudy is everything in this purple color, so it's kind of visually where you see clouds in the image. Probably clear is over the sun glint, because it's bright and they think it's probably not a cloud, but they know cloud detection is difficult over sun glint. So they say probable rather than confident. And probably cloudy and probably clear are otherwise tend to be found around the edges of cloud systems, where it's kind of more of a judgment call. Maybe there's some broken cloud, maybe there's some cloud filaments in there. So we have this four-way categorization, but we can easily transform it to a binary one if we need to, which some applications do. And like I said, this is basically a series of threshold tests. So some people spend a lot of time manually looking at images and making histograms of reflectances or temperatures or ratios between those and saying, what are the typical values of this parameter for a cloudy scene or a clear scene? And they get histograms like these, and they draw some lines at various points. And then what they say is, if I'm above this line, I'm going to say it's cloudy. If I'm below it, I'm going to say it's not cloudy, or vice versa. And if I'm in between these two lines, I'll say this test says there's some probability that it's a cloud between 0 and 1. So what they do is they have a whole bunch of tests, and they put them in different groups depending on what sorts of cloud features the tests are good at identifying. And for Modus and Vias, they have these 5 different groups. In each group, they then find a test that they have the strongest reliability and the one with the most extreme probability, close to 0 or 1. And they say, okay, this is the probability from this group. Then they define this Q-score, where they combine tests from all the different groups together and get this overall probability of cloudiness, which then determines your cloud mask. Now, unfortunately, with PACE OCI, without the thermal bands, we lose an awful lot of these tests. So we're basically only relying on 2 of the 5 groups of the tests they have in MODIS and VIIRS, which is partially why we're looking into alternatives such as the neural network method. So these solar-only tests still work pretty well over water. Here I've got a true color image. This is the MODIS classification, and this is what happens if you run the MODIS mask but switch off all the tests that OCI won't do. And if you kind of squint, they're really quite similar. Most of the difference is in these areas where the mask is not confident but is probable. So maybe it's good enough in a lot of cases, but it would still be nice to do better. If you go to scenes over land, like this one over China, you can see there's a lot more disagreement between the two. So here are some aerosols along the southeastern coast of China. And the MODIS mask thinks they're probably a mix of probably clear and isolated pockets of cloud. Whereas if you don't have the thermal bands, you get a few misclassifications where it thinks this is definitely a cloud and a few where it thinks this is definitely clear. So it's a lot less robust over land than over water. So that's kind of means this is still a bit of an area of research, though I'm not really too concerned because while thermal bands are super useful for a lot of cloud remote sensing, we also have decades of experience with sensors without any thermal bands, and they still do a pretty decent job overall. So we can get it working in time for launch. It just means we can't use the heritage algorithms as is. So next is the cloud's top pressure, which, like I mentioned earlier, is a new algorithm because of this lack of thermal bands. Now, the NASA Worldview color scheme for this, it breaks down its shading by whether it's a liquid water cloud or an ice cloud. So liquid water clouds are in these warm tones over here. Red means very low, and kind of yellow means higher up. And then these ice clouds are in these blues and these purples as well too. So what you kind of see if you look at this visible image is that this big swirl of clouds here, and then this one here as well. And just looking with your eyes, you can't really see, are they at the same height? Are they part of the same system? Maybe, maybe not. If you look at the right-hand side, you can see this one here is liquid water clouds. They're pretty close to the surface. So that's the sort of thing like a stratus cloud. If you'd go outside, the sky would be dark. The cloud is not too far above your head, so you get a bit claustrophobic. Whereas this system here is much higher up and it's made of ice. This is something you see way up in the sky above you and you probably don't care about, but it might rain in an hour or so. So the purpose of cloud dot pressure is obtain the estimate of the altitude at the top of the cloud. We can't say about the base of the cloud, just about the top. And again, even though we're working in pressure coordinates, it's pretty trivial to transform to temperature or altitude using meteorological profiles, which we can get from forecast models or reanalysis models. I just put on pulled on the US standard atmosphere profiles from here. So as you go up in the atmosphere, it gets colder roughly linearly in the troposphere, and the pressure drops roughly logarithmically with height in the troposphere. So it is, in most cases, but not all, a one-to-one relationship, which is nice. There are things called temperature inversions which break that, but we can forget about those today. So how does it work? Well, OCI samples these strong gas absorption features. Amir showed some of those in his presentation. His atmospheric correction is about ignoring them. My cloud dot pressure is about using them. And we're specifically using a feature called the oxygen A band. Now, oxygen is about 80% of the atmosphere, and it's well mixed, which means the proportion of oxygen in the atmosphere is roughly the same whether you're at sea level or whether you're really high up. So the idea is if you have some spectral area where oxygen or any other well-mixed gas absorbs, then if you have something that's sensitive to changes in the apparent absorption, you can get kind of a good estimate of what pressure that feature is at. So here I put the spectral response functions for a bunch of the OCI bands near this region in red, and the shading in various colors shows the gas absorption features, and this gray here is the oxygen A band, very sharp, lots of lines. There's also ozone, which in this area is very weak and very flat, so you can barely see it, just not even worth trying. And there's water vapor, which creeps in at the end here, and it's also kind of a problem. As well as OCI, I've shown similar spectral response functions for the Sentinel-3 ULCI instrument. It's a European instrument. We have access to the data, which is great. And they're kind of similar enough for our purposes, in that they both have these kind of observations in this window region here, where there is no oxygen absorption. And then they've got a few bands within the oxygen A band here, sampling different levels of absorption. So the idea is we're combining channels outside the absorption feature, which is what we call the window, the ones right inside it, where we get differential sensitivity to feature height. So, there's a typo here. So what we're going to do is simultaneously determine the cloud optical thickness, the cloud top height, and the surface albedo from the hyperspectral measurements in this region. We have to have a very strong prior constraint on the surface albedo, though, which we can get from any number of sources. So what happens if cloud optical thickness increases here from dark to bright colors? The whole spectrum gets a lot brighter. Unfortunately, if you increase the surface reflectance, you see the same thing. So a brightening surface looks the same as a brightening cloud in this region. And that's why we have to know or have a good idea what the surface reflectance is beforehand. If you change the cloud altitude, the cloud top height, in these window regions, the signal doesn't really change much at all. So this window is really only sensitive to the cloud optical thickness and the surface properties. However, you get this filling in of the absorption lines within the A band itself, and that's because clouds are really bright, they're scattering objects, so when you put them in the atmosphere, they stop the atmosphere below it from absorbing light, so you get this filling in of the feature. Unfortunately, the cloud vertical extent also matters. If you have a cloud that's really compact, it looks very different from a cloud with the same amount of water that's spread throughout the column. And again, that's because oxygen is well mixed. So we have to make some assumption about the cloud vertical structure. But when we've got an assumption about this, and we've got an external guess on this, we can use these measurements to determine these two things. And it really works. We've run it on this European Sentinel-3 ULCI data. This is just one example from one of our validation sites, which is ARM, that's a Department of Energy facility in Oklahoma. So there's a low stratus cloud deck over here. There's some high cirrus clouds over here. And this area is where you get two cloud layers overlapping. It's what we call a multi-layer system. This is the cloud top height. So purple means like 0 to 1 kilometers. And this one is kind of more like 9 kilometers. So this thick stratus layer is very close to the ground, maybe a kilometer up on the top. This cirrus cloud is more like 6 to 9 kilometers above. And where you've got this kind of multi-layer system where the two merge, you determine a height that's somewhere in the middle, which is not necessarily ideal, but that's kind of the limitations we've been dealing with for the past 20, 30 years. We also get this estimate of cloud optical thickness, although it's not necessarily the main one we'll use for PACE data analysis. And a measure of this thing called the cost function. It's like a chi-square test that tells us how well the measurements fit the solution. So if this is really, really high, you think maybe there's some problem with this pixel. So finally, when we have all that, we can determine cloud optical properties, which is of optical thickness and effective radius. Behind me again is the MODIS true color and then a MODIS optical thickness map. There's not really too much to say about this, so I'll just skip. So again, the purpose of this is determine the strength of cloud light extinction and the cloud droplet size. And from those, you can also determine the amount of total amount of water within the cloud. And it's last in the processing chain because first we have to have the cloud masks know which pixels are cloudy. We have to know the cloud height to correct for absorbing gases. The same we do for ocean color. You have to correct for things like ozone and water absorption above the clouds. So when we've got that, we get this. On the right-hand side here is a MODIS image of a marine stratocumulus deck. I think it's somewhere in the Pacific, though I'm not sure. And on the bottom is a map of the cloud droplet radius retrieved from MODIS. And what's fun about this is these streaks are where ships go. So the ship's exhaust pumps out a lot of water and a lot of aerosols, and this affects the clouds. So you get changes in the droplet size in the clouds, which affects things like how long they last for, whether they rain or when they rain. And you can't see them so strongly in a visible image. But it can have pretty significant effects on the water cycle. So this is something that's really important for climate purposes and understanding aerosol cloud interactions more generally. So this is an approach with 30 years of heritage, and it's really conceptually not too difficult. The idea is you took two wavelengths of light at once. You pick one wavelength where clouds are not absorbing, where they just scatter light. Typically that's in the visible or the near infrared. And then you pick one wavelength where clouds don't scatter light very much and they mostly absorb it. And that's typically in the shortwave infrared. And you can make these plots. Some people call them Nakajima King plots after the authors of one of the early major papers on this. And the idea is you have this non-absorbing band here, 870 nanometers. And these kind of vertical lines are lines of increasing cloud optical thickness. And on the y-axis, shortwave infrared, 2.1 micron reflectance. And these kind of horizontal lines are ones of a decreasing particle size. So the higher the optical thickness, the further to the right you are. And the smaller the particles, the further up you are. And because these lines are roughly orthogonal, so they're roughly at right angles to one another, it is often a fairly direct lookup between these two channels and these two parameters, which is really nice. The other thing that's relevant here is the cloud phase, so liquid or ice crystals. The plots for the two look fairly different because the two have different scattering properties. So if you find yourself up here, you can be pretty sure you're looking at an ice cloud. If you find yourself down here, the liquid cloud. You find yourself down here, you're pretty sure you're looking at an ice cloud. And if you're somewhere in the middle, it really could be either one, so you've got to use some other methods to try and guess what you're looking at. And the final note on that is MODIS and V is our heritage. They tend to use not just one shortwave infrared band, so not just one of these absorbing bands, they use several, and we do the retrieval for each of them. And that's because the signal in those bands depends on the size of the clouds, the droplets within the clouds. And that's because the absorption is driven by this droplet volume, or rather the droplet surface area. Because the bigger something is, it affects how efficiently it absorbs light. And as the absorption coefficient of water varies as a function of wavelength in the infrared, if you look at multiple different shortwave infrared bands, you can see at different distances into the cloud, because real clouds often have different droplet sizes at the top from the base. So the idea is if you do the retrieval multiple times and you use different shortwave infrared bands each time, then if you get the same answer or if you get different answers, it tells you something about what might be the vertical structure of the cloud droplets within this cloud, which can be useful, for example, because if it's raining or if it's going to rain, you can get very different profiles to if it's not. So that is about 35 minutes, this is telling me, sorry, on cloud remote sensing from PACE OCI. And the main message is that this has been done for decades and decades and decades. It's very well understood. So going into PACE launch, I think we should immediately be making useful data products that people know how to use and can have a decent degree of trust with. The one exception here is this cloud top pressure algorithm, which is fairly new to us, but there is a strong heritage from that technique within Europe and then more recently in the US with another instrument called EPIC that we won't talk about. And again, this is all going to be processed on single pixels at a time, globally over land and ocean and sun glint and snow and ice, just not at nighttime. And that is more or less it. If you want to read more, there's these references which you can look up later, or if you have any questions, I can take them now. Okay, great.
Thank you, that was really cool. I have a question about how to deal with or anything new about that issue, I guess.
Yeah, you're right. It's a difficult problem and it's a perennial problem because coasts are very complicated for so many reasons that you don't even know how much land or how much water is in here. And the pixels around coasts tend to have really variable surface properties, very variable depths, and these kind of microclimates where you can get these thin fogs. The short answer is we don't have a good solution. The less short answer is there are some ideas for things you could do. One approach is to try and treat them as if it were an aerosol and do an atmospheric correction through it. I think the quality of those pixels will always be suspect, but with new approaches like the multi-band atmospheric correction, we can probably do a better job correcting them than we could in the past. With PACE OCI as well, given the higher signal to noise of the shortwave infrared bands compared to the heritage, I think there's maybe more hope that the pixels will be less bad than they are, but I think fundamentally that's something that's not easily fixed by remote sensing in general, unless we can go to somehow finer spatial resolutions, or we can get an active sensor like a LiDAR pointing at the right place. Yeah.
Does the confidence estimate that the cloud mask is doing, like, does that identify that patch at all? It seems like it should.
Sometimes it does, sometimes it doesn't.
Yeah, it should. And we're hoping that this neural network method that we're going to try is going to be more robust in some of these cases, because one of the advantages of the neural network framework we want to use is that when you're training a binary classifier like that, the network actually returns to you should be interpreted as a probability of classification A or not A. So part of our evaluation, we're going to be using, like, if the network says my confidence is this %, then is that the real likelihood that this is the correct answer or not? So again, maybe in the next year or so, we'll have a better idea about that. Yeah. Anyone else? Great. I think we're done then.